Check this out. We've got something really fun today. This is so amazing. Oh man, again? 8.3 Log Laws. Using a calculator, find the values of all of these here and record it to 4 decimal places would probably be good. And then what pattern do you see? So pause the video and do that. I've color-coded the ones that are the same, and we can observe that when we're adding two logs that have the same base, we can be rewritten as one log with that same base, in this case base 10 for everything here, and the two arguments are multiplied together. So 2 times 3 is 6, and this one here, 3 times 4 is 12. Now this is probably pretty helpful because this is a lot simpler than this. Why does this work? Well, let's set it up. We will just let m equal c to the power of x and n equal c to the power of y. When we rewrite those two equations into logarithmic form, it equals this, and we're going to use that later on. First of all, we're going to multiply m times n. So c to the power of x times c to the power of y. And then using our exponent laws here, this has the same base, so we can add the exponents. And then from here, we can rewrite this into log form. So the base of the exponent is c, so it becomes the base of the log. M and n become the argument of the log, and the exponent is freed up. And then we go back, at this step, we go back and we replace x with log base c of m, and log base c of n replaces the y. And this is our first log law. Do the same thing for these examples here and write down the pattern that you notice. Again, I've color-coded the ones that are the same, and there's definitely a pattern here. If we're subtracting two logs that have the same base, it's the same as one log with the first argument being divided by the second argument. So 64 divided by 4 is 16, and 48 divided by 2 is 24. And so you can see those two are the same. Why does this work? Well, it's almost the exact same setup as last time. We got m is equal to c to the power of x, n is equal to c to the power of y. That was all the same. It's just this time we'll set it up with division. And we use our exponent rules, this time with dividing. That means we subtract x and y here because they have the same base. From this step, we rewrite into logarithmic form, and then we sub out x and y using these equations that we had at the very beginning. And that is our second log law. Let's try that again with these examples here. Evaluate all of these log expressions and write down what pattern you can find between these. There is definitely a pattern here. When we have an exponent on the log's argument, we can move that exponent down and it can become a coefficient in front of the log function, and those two values remain equal. Both of these are the same because 2 to the power of 4 is 16 and 4 squared is 16. Let's see why this works. If we have m equals c to the power of x, and this time we only need this one, we can rewrite this in log form, which we'll use at the very end here. We're going to raise both sides of this equation to the power of p. And then using our exponent rules, we know that we're going to multiply x and p here. So we're going to get c to the power of xp. Now we're going to rewrite this into log form using the c as the base. It is possible to rewrite it using the m as the base, but we don't want to do that. We want to get into this form. So c is the base, m to the power of p is our argument, and xp here is the exponent that is getting freed up. Now, right at the end here, I'm going to replace x with this expression right here. And so you can see that if m has an exponent of p, it does in fact equal p as a coefficient in front instead. And the other way would work too. If we had a coefficient that we didn't want to we didn't want in front, we could move it into the exponent position. Just be careful that the exponent of the argument needs to be the exponent of the whole argument and not just a part of it. So this is our third log law. Now we can change the base of a log if we want to. We'll set this one up, m is equal to c to the power of x, and we'll take the log of both sides. And we can choose the base that we want, so I wrote a here to signify whatever base we're choosing. Now we're using the third log law. We have an exponent here on our argument, so we take that exponent and we move it to become a coefficient. Now we divide both sides by log base a of c, and we're just left with x on this side, and we replace that x with the original equation that we started with rewritten into logarithmic form here. So x is equal to log base c of m. And you can see that now we've changed the base. Our base was c and our argument was m, and now the argument for the numerator's log is m, and the argument for the denominator's log is now c, which was the old base. And we've introduced a here, a base of our choosing. Let's see how this might work with some examples. If we have log base 5 of 26, maybe we have an older calculator where we can't change the base, but we do have a base 10 function. So we could rewrite this as log base 10 of 26 divided by log base 10 of 5. Let's try another one. Let's try log base 5 of 2. Let's rewrite this, but I want a base of 2 instead. So we'll go log base 2, that's the one I chose, and the argument will be this 2 here. And in the denominator, I go log base 2, because that's the base I chose, and the old base, which was 5 here. And we could do something cool. We can simplify this, because log base 2 of 2 is just 1, and notice that the original base was 5 and the argument was 2, and we've switched those and it became reciprocated here. We want to expand these logarithmic expressions and remove any exponents and radicals. The first one, we just want to expand it, so this could be written as log base 5 of x. Now, since we're multiplying by y here in the argument, then we could say plus log base 5 of y. And then we're dividing by z, so it would be minus log base 5 of z. Let's try the next one. First, we will remove the radical. So we could rewrite this as log base 5 y to the power of 1/4, because the index of the radical becomes the denominator of the exponent. We'll say divided by x z. Now we'll expand this out. First one would be log base 5 y to the power of 1/4. We're dividing by x, so that would be minus log base 5 of x. And we're dividing by z, so that would be minus as well, log base 5 of z. Now we want to get rid of this exponent here, so it's the exponent of the argument here, so it can be moved down to become a coefficient. So 1/4 log base 5 of y minus log base 5 of x minus log base 5 of z. Now lots of students get mixed up here. They think because they subtract the x or divide by x, then this one should be positive, but we're dividing by x and we're dividing by z, so they're both negative. If you did this one minus and then use brackets around it, then you might have a plus there. But as soon as you distribute in that minus, they'd both be minus, like this. Next one, let's get rid of this radical first. So we've got log base 7 x to the power of 1/3 y squared. Now let's break these two pieces up here. So we've got log base 7 x to the power of 1/3, and they're being multiplied, so plus log base 7 y squared. Now we want to get rid of the exponents, so we'll just drop them in front. So 1/3 log base 7 of x plus 2, dropping that down in front, log base 7 of y. This one here, we can first get rid of the radical, log base 7 of 7 over x to the power of 5/3. Breaking this one up, we've got log base 7 of 7 minus log base 7x to the power of 5/3. Now log base 7 of 7 is just 1. So this is 1 minus, we'll drop this exponent in the front here, 5/3 log base 7 of x. And let's get rid of the radical here. Log x to the power of 4 over y, z to the power of 1/2. That's only z's exponent, not y's. We'll break this apart. So we've got, and let's drop these exponents in the same step. 4 log x minus log y minus 1/2 log z. We want to evaluate these expressions without a calculator, and if I just looked at the first one here and looked at the individual logs, it wouldn't be possible. So 3 to what exponent gives me 6? I don't know, 1 point something. But these are definitely not good numbers to work with. Let's consider the whole expression though and use our log laws and see what can happen. We've got the same base for all three of these, so we could rewrite this in 1 log. So this is 6, and since we're adding here, we could multiply our arguments here. And we're subtracting this one so we can divide that argument. So this is now all in 1 log. Now we can do some quick math here. 6 times 15 is 90, divided by 10 is 9. So we've got log base 3 of 9. Now we can do this because 3 to what exponent gives me 9? 2. So that's one way to do it. Another way to do it is to break it all apart. So somebody else did this. You know 6? 6 is 2 times 3, so I could actually do that. I could say that this is log base 3 of 2 plus log base 3 of 3. Okay, because 2 times 3 gives me the 6. Now I can break apart 15 and 10 as well. So this would be log base 3 of 5 and log base 3 of 3. Now I'm going to break apart this term, minus log base 3 of 5 minus log base 3 of 2, because 5 times 2 is 10. Okay, now when I look at all of these terms, it actually looks worse for a second, but log base 3 of 5 minus log base 3 of 5 actually cancel out here. And log base 3 of 2 and log base 3 of 2, they cancel out as well. So the only thing we're left with is log base 3 of 3, which is 1, and log base 3 of 3, which is also 1. And so we still get the answer of 2, using a slightly different strategy here. Let's try the next one. Next one, we've got a base of 3, and 9 and 3 here can be also written as a base of 3. So let's try rewriting those. We've got log base 3. 9 is 3 squared, and the square root of 3 is 3 to the power of 1/2. So when we have an exponents here and they have the same base, we can add those exponents. So log base 3 of 3, and this would be 2.5, or 5 over 2 if you prefer. Now using that third log law, we can take this exponent and drop it down in front. So that would be 5 over 2, and we're left with log base 3 of 3. And 3 to what exponent gives me 3? 1. So this whole thing just equals 1. So the answer is 5 over 2. For the next one, we could do something very similar to this, but let's try splitting it up just for some variety in our approach. So we've got log base 7 of 7, and since we're multiplying in here, that would be the equivalent of adding here a different log base 7, and the root 7 is in here. So in the same step, I'm just going to change that radical to an exponent instead. Now in the next step, we've got log base 7 of 7, so I guess I can reuse that, and drop this exponent down, 1/2 log base 7 of 7. Now log base 7 of 7 is just 1, so we've got 1 plus 1/2, which is 1.5 or 3 over 2. How about this one? Let's rewrite this one, and we'll put this together. They've all got the same base, so I think the easiest would be to put it together here using the same base. We've got 1,000, we've got minus 4, so that would be divide by 4, and then we've got minus here again, so that would be like dividing by the argument of 2. And then we've got 1,000 divided by 8, which is actually 125. And 5 to what exponent gives me 125? That would be 3. All right, next one. This one's got a couple of different things we could do again, but let's try writing everything together here. So let's get rid of the coefficients, move them up into the exponent. So log base 2 of 12 squared. So the coefficient went up there. Now let's get rid of the brackets. We've got minus here. We've got log base 2 of 6. And this one here, we could say minus because I distributed in the minus sign. And the 1/3 becomes the exponent up here. So log base 2 of 27 to the power of 1/3, which is the same as cubed root. Now this one here, we've got the same base for all of these now. So I'll do one more step and then we can put them together. This is 144 log base 2 of 6, and the cubed root of 27 is just 3. So now I can say log base 2 of 144, put these all together, divided by 6, and this is minus 2, so divided by 3. So 144 divided by 18, and that gives us 8, and that makes this question doable without a calculator because 2 to the power of what gives me 8? That would be 3. And last one here, let's try again putting all these coefficients as exponents instead, and then we can combine this up. So we've got log base 3 of 6 squared minus log base 3 of 64 to the power of 1/2 plus log base 3 of 2. Let's evaluate these and then put all this together. So we've got log base 3 of 36 minus log base 3 of 8 plus log base 3 of 2. And put it together into 1 now. We've got 36. We want to divide by the 8 because we're subtracting, and we want to multiply by 2 because we're adding that. So this would be 72 divided by 8, and that would be 9. So we've got log base 3 of 9. And 3 to what exponent gives me 9? Well, that would be 2. We want to simplify these expressions and also state the restrictions on the variables. Now, if we have a log with a positive base, and we're just using positive bases in this course, then this argument needs to be positive as well, because 7 to any exponent is going to be still positive. There's no exponent we can give 7 that will turn it into a negative number. So they must both be positive in this course. For the first one here, we could either create all coefficients or all exponents. So let's do it with all exponents. So we'll keep the first one the same here, x to the power of 2. And we'll keep the second one unchanged as well. And this is minus 5 over 2. So let's put that as an exponent instead. So x to the power of 5 over 2. Now let's use our log laws and combine up these because they all have the same base. So we've got log base 7 of x squared. Now this is plus, so we're going to multiply. And this one's minus, so we're going to divide that argument. Okay. Now we use our exponent laws to simplify what's going on inside here. We've got log base 7, and in the numerator we have x cubed. And we're going to subtract 2.5. So 3 minus 2.5 is x to the power of 1/2 is left. Let's try this the opposite way. We'll try it with coefficients instead. So we'll put an or here because you don't need to do it both ways. Instead, let's move this to be a coefficient. 2 log base 7 of x plus log base 7 of x, and this one here is already a coefficient, so this one we leave, minus 5 over 2 log base 7 of x. And log base 7 of x is common, so we can actually just factor it out and add up the coefficients, or subtract them. So 2 plus 1 minus 5 over 2, and these are all log base 7 of x's. And when you add 2 plus 1 minus 2.5, you get 1/2. And might for a second look different, but using that third log law again, we see that this can be moved into the exponent position, or this could be moved down to the coefficient position. So these two are the same. Now let's look at the restriction on the variable. For this one here, we need that x squared is a positive number. Now, it's always positive except at 0, so x cannot equal 0 here. When we look at this one, though, x isn't squared, and same with this one, and so this one is just x is greater than 0, so that it's always positive. Remember, 0 is not positive, so x needs to be greater than 0. So that's the restriction on our variable. We want to do the same thing for these two expressions here, simplify them and state the restrictions on the variables. The first one here has a lot of coefficients, and so I'm going to just use those coefficients. So the first one we'll leave as 4 log base 3 of x, and then we'll minus, now this is a log base 3 of x, and this is 5 log 3 of x, so that put together is 6 log base 3 of x. Now 6 times 1/2 is 3, so we'll just do 4 log base 3 of x minus 3 log base 3 of x. So 4 minus 3, and we can do this because they're both the same logs here. So 4 minus 3 is just 1. So we're just left with log base 3 of x. What's the restriction on the variable? Well, we have x in here, and so that means that x needs to be greater than 0. That's our restriction. The next one is going to be a little bit more difficult, especially for the restriction. So let's put these together using our log law. We've got log base 2 of x squared minus 9, and I'm going to factor that into x minus 3 and x plus 3. And this is minus, so that means I'll be dividing by this quadratic here. And I'm also going to factor this quadratic here, so put some brackets to show this is all together. This would be x minus 3 and x plus 2 when I factored in. Now you can see that the x minus 3 and the x minus 3, they can be canceled out, and I'm left with log base 2 of x plus 3 over x plus 2. Now that wasn't too bad, but the restriction is a bit more difficult. So the restriction for this one means that x squared minus 9 needs to be greater than 0. And the restriction for this one is x squared minus x minus 6 needs to be greater than 0 as well. Let's look at these two independently, and then we'll have to put it together and make a rule that will work for both of them. Let's do it graphically, since that's the easiest. We've done quadratics, we know what they look like. This one opens up and it has x-intercepts at -3 and +3, and it looks something like this. Now where is it positive? That would be when x is less than -3 and when x is greater than 3. So that's the two restrictions coming from this first one. Let's see what the second one has to say. When we look at this one graphically, we can look at the factors that I used here. We've got x-intercepts at +3, and we've got an x-intercept at -2. And this one also opens up, and so it looks something like that. Where is this one positive? When x is greater than 3, and when x is less than -2. Now this one is a little bit less strict than this one. This one is less than -2, but this one says less than -3. And they both have greater than 3, so they're in agreement there. So we need to go with this as our restriction because it satisfies both. It satisfies this one's got a bit extra, but we can't use it because this one doesn't use it. The intensity of sound in decibels is defined as decibel is equal to 10 times log base 10 of the intensity of the sound divided by the I naught, which is 10 to the power of -12 watts per square meter. A chainsaw is 85 decibels, and a portable media player can play sound at 110 decibels. How many times more intense is 110 than 85 decibels? So first let's find the intensity of the noise for a chainsaw. So we have that it's 85 decibels, so I'll put that in there for decibels, equals 10 log. I'll put the I here with the subscript C for chainsaw, and then divided by I naught. Let's divide both sides by 10, so we get 8.5 is equal to log IC over I naught. And then we can rewrite this into exponent form. The 10 here is the base of the log, so 10 to the power of 8.5 equals IC over I naught. And then multiply both sides by I naught, so we get the intensity of a chainsaw is 10 to the 8.5 times I naught. And I know I'm given I naught in this question, but I'm not going to put it in here for part A anyways, because I don't need to. The next one, let's find the intensity of this portable media player. 110 is equal to 10 log I, and we'll say that this is a P for portable or player, whatever, over I naught. Do the same sort of algebra steps so that we get 11 is equal to log IP over I naught. rewrite this into exponent form. 10 to the power of 11 is equal to IP over I naught. And then multiply both sides by I naught, and we get the intensity of sound for a portable music player is equal to 10 to the power of 11 times I naught. Now to find how many times more intense is 110 than 85, we're going to take this one and divide by the intensity of the other one, the chainsaw. So this will be 10 to the power of 11 times I naught, and this will be 10 to the power of 8.5 times I naught. And the I naughts cancel, and that's why I never needed them anyways. This right here, we can use our exponent rules, and we get that 10 to the power of 2.5 is how many more times intense is the portable player than the chainsaw. And we can see that this makes sense. This is about 316 times more intense.